Hey, this is Munawar, Chief Technologist of OpenRefactory. Last week, I announced in a video that I plan to go through and do this test drive of bug detection and fixing tools, specifically to understand the benefits that you get from these bug detection tools and the cost that we have to pay in order to triage the false positives. Today is the first of this series of videos that I plan to do. Today I'll be test driving Semgrep to understand its bug detection capability for Golang. I'll be running Semgrep on Kubernetes, which is the most well-known open source Go application that's out there. Kubernetes is maintained in GitHub. I did not run Semgrep on the current master branch of Kubernetes. In order to make things interesting, I went back in time and ran Semgrep on a version of Kubernetes which had a well-known data race bug in it. Let's see if Semgrep can find this bug and also what else does it find on that particular point of time. The link to the particular commit will be given in the description section of the video. Semgrep identified 808 bugs in that Kubernetes version. However, not all of it is associated with Go. A lot of the bugs were found in YAML files, and in this video I will ignore them. I'll just focus on the 157 bugs that Semgrep identified on Go code in Kubernetes. The most common kind of bug reported by Semgrep was about using the RAN library. Let's look at one example. We see that Semgrep flags a bug just because the RAN library is imported. If we dig a little deeper and do a search and identify where this library is used, we see that this is used in a function called resync period, where the RAN library is used to create a random interval for the resync function. Typically, a more secure version of random, which Semgrep is suggesting, is needed for cryptographic operations. In this case, this is a perhaps benign case of randomness, so the RAN library works just fine. We will categorize this bug as a WONTFIX bug. Next, we'll look into another category of bug, which is listed by the missing SSL min version rule of Semgrep. Here, the minimum version for TLS is not specified explicitly in the TLS configuration. Semgrep is just looking at the structure of the TLS configurations and raising a bug just because min version is not there. In this case, perhaps this is done intentionally because Kubernetes wants to support a wide variety of legacy clients. However, we don't know this, so we will file these 15 bugs as something that needs to be looked at. These are all medium severity bugs as specified by Semgrep. Now let's look into another category, which is about iterating over an empty map. Let's look at one example. Here, Semgrep flags completion shells as a map that is perhaps empty when it is being used by the function getSupportedShells, which has a for loop to iterate over this map. Typically, this is a benign issue because in the worst case, the for loop will just iterate over an empty map and nothing will happen. However, we see that the map is perhaps populated in the runCompletion function, and we don't know whether runCompletion runs before getSupportedShells. Therefore, by the time the for loop is running, perhaps the map is already populated. Because Semgrep is only looking at structural constructs, it is raising bugs everywhere where it finds a map. We will count these bugs as false positives. Okay, enough of the low and medium severity issues. Now let's look into an issue that Semgrep has flagged as a high severity bug. In this example, we see that in the function run etcd control command, there is a command that is created from input that is coming from the command line. However, for Kubernetes, because it takes input from the command line, the users of the command line are probably trusted. So the attack surface is not there. We'll mark these as WONTFIX issues. Semgrep identified 10 issues because weak cryptographic algorithm MD5 was used. However, when we looked into one example, we identified that hash addresses function, which was using this, was eventually being used to create a key for a hash map and then doing lookup into that hash map. It was not used in any cryptographic operations. Therefore, this is perhaps a benign use. It is faulty for a tool to report a bug just because MD5 is used. You need to identify the context, whether this is used in a cryptographic operation before raising a flag. We will categorize these as false positives. Later, we found 3 similar cases where Semgrep reports SHA-1 algorithm being used, but those were also benign cases. Next, Semgrep files a bug regarding unsafe string to integer cast. However, if we look at the code where it identifies the bug, we see that every point after this conversion of string to integer, there is an error case that is checked. Therefore, these are all false positive. Next, there's been a bunch of bugs that have been flagged by the import text template rule. But these are only looking for the presence of the template library that are being imported. It is not looking at the use cases of those library functions. So we'll ignore them. Instead, let's look into the next 2 categories. The first is about no direct rewrite to response writer rule, and the second are found by no direct fprintf rule. If we look at an example of the second kind, we see that the function handlefunc does have a use of fprintf, but it is writing mostly values that are controlled by the programmer or hard-coded values. The same happens for the first rule's case as well. Here's an example in the serve HTTP function where the write is happening not with value that is controlled by an attacker, but with value that is controlled by the programmer or hard-coded values. So all of these are counted as false positives. Next, let's look into the bugs that are found by the bypass TLS verification rule of Semgrep. In the create proxy transport function, we see that there is a TLS config that is created with insecure skip verify set to true. This is perhaps intentional, but we don't know why the developers chose to do so. Therefore, we'll count them as true positive for now. These are all medium severity issues. Semgrep found 7 bugs following the unsafe reflect by name rule. If we look into one example, we see that filled by name is being used from the library and Semgrep is flagging that. However, this is perhaps being used intentionally by a portion of the code that is introducing the fuzzing capability. This part of the code requires access to the methods, and therefore it is doing a lookup using the reflect library. We will categorize these as false positives. Next, Semgrep uses the gRPC server insecure connection rule to find 4 bugs. These are cases when Semgrep identifies an insecure gRPC server without grpc.creds or options with credentials being specified. We see that all 4 of the cases that were identified were in files that probably have some examples or some fake runtimes. As in, the name of the file that is shown here is fakeruntime.go. Therefore, all 4 of these are WONTFIX issues. Similar thing happens for the 4 bugs that are identified using the avoid bind to all interfaces rule. They are also in test code, and therefore all 4 of them are WONTFIX issues. Phew, thanks a lot for your patience. I tried to be as brief as possible while explaining the different kinds of bugs. However, it is turning out to be a pretty long video. So instead of looking into the long tail, let's just summarize the results in a Google Sheet. This Google Sheet will be publicly available and the link will be posted in the description of the video. Before moving into the result summary, let's look into some of the other bugs that are of high severity that Semgrep found not in Go code but in other kinds of code. Semgrep detected 65 cases where a possible private key was detected. But if we look into this, we find that all of them are found in some sort of testing code. The same happens when Semgrep identifies some secrets in the code. However, if we look into that, we identified that these are found in comments of the code, not in actual code. So Semgrep is possibly just using regular expressions to flag these. And it is discounting the fact of what is supposed to be in the source code versus what is supposed to be in the example. So, what did we get? Semgrep reported 157 issues. Among them, we categorized 24 of them as true positives. These were all medium severity issues and were related with cryptographic operations. We're not 100% sure whether these are all actual bugs, but at least they deserve some attention from the maintainers, who have the domain knowledge and can arbitrate whether these are true positives or not. There were 57 WONTFIX issues and 76 false positives. Most importantly, the data race vulnerability that we know is there in the code was not detected by Semgrep. If we assume that it takes about 10 minutes to triage a bug, it takes about 22 hours of time that is wasted triaging the false positive and WONTFIX bugs in this case. Assuming a loaded labor rate of $130 per hour, it takes about $2,800 to triage the results of Semgrep. And again, the result missed a critical bug. Next week, we'll be test driving another bug detection tool. I hope you'll find that interesting too. But meanwhile, I'd appreciate your feedback on this video and how we can improve the analysis.